The last class, you will remember we discussed about the diffraction phenomena using Huygens and Fresnel principle. So let's make some quick revision on diffraction. So let's say I'm sending out the wave through a small gap over here. You can see the wave that is coming out is circular in shape, right? That's a linear wave, but the wave that is coming out is circular in shape here. And this phenomenon is what we called as diffraction. And we have learned that larger the wavelength, larger the diffraction, also smaller the slit width, larger the diffraction. So we'll do one thing, we'll take a larger slit width and we'll create a wave front. Look at this here, look at this, that's straight, curve, right? Curve, straight, curve. Let a wave pass through, look at this here, curve, slightly straight here, and then curve. What if I make the slit width negligible? Now let's look at this one here. Look at this, that's pure curve form, right? It's a pure curve here. But whereas when slit width is larger, you can see curve, straight, curve, right? I'm just showing once again. Look at this, I'm taking a smaller slit width and just look at the wave that is going out. Look at that, that's curved. Let me just send it, or let me slow down and show you. Look at that wave, that's pure curve here, right? It's a pure curve. That's what we have learned in the last class, that smaller the slit width, greater the diffraction. Here if you look at this, flatten here, curved at the edges. So that's all about diffraction that we have already learned. Let's now move to the next topic, that is double source interference. So what we have learned under diffraction, that when you send out a light wave, it doesn't just go straight and hit at one spot. Instead, the ray may go and hit the multiple spots on the wall, right? This is something which you already learned. Now what if I have two sources of sound? Let's say I have two speakers in the room. That's a speaker number 1, I'll call it as S1, and the speaker number 2, S2. Now the sound wave radially go outward in every direction like this. Similarly, S2 will also produce sound wave that radially, let me change the color. S2 also produces sound wave that radially goes outward in like this. So you can see at each point, look at this point here, that you know that the wave fronts are the line passing through crest. That means this is a crest of a blue wave and that's a crest of a red wave. So this point is where the crest of a blue wave overlap with crest of a red wave. That means this point is a constructive interference, right? Crest meeting crest, constructive interference. What about this point here? The crest of the blue meeting what? Trough, because the region between two consecutive crests is a trough, right? The center between two consecutive crests is a trough. So this is the region where you have a trough of a red meeting crest of a blue. So that means this region, this point is going to have a destructive interference. So that means two sources causes interference, right? And you have both constructive and destructive interference happening and so on. So let's look at this image here. So you have a source S1, a speaker, maybe you can consider sound source S1 and sound source S2. The sound source S1 sending out the wave outward, sound source S2 also sending out the wave outward. I'm talking about a random point A. So random point A is where you're having a constructive interference, but why? Because you can see crest meeting crest. Similarly, look at any other point here, look at this point here. That point, I'll call it as B, is causing destructive interference. Why? Because crest meeting trough. Yeah. So look at this here. This point B, constructive, crest meeting crest. Here point C, constructive, crest meeting crest. Point D, destructive, crest meeting trough. Point E, destructive, crest meeting trough. So I'm writing down constructive, constructive, destructive, destructive. But if you observe in all the images here, that for the point B where the constructive is happening, source S1 wave, the wave from the source S1 has to travel 3 times the wavelength. So why? Look at this one. That's one wavelength, lambda distance traveled, 2 lambda distance travel, 3 lambda distance travel. So source S1 wave travel 3 lambda to reach point B. Similarly, the wave from source S2 has to travel 1 lambda, 2 lambda, 3 lambda and 4 lambda. So wave from source S2 has to travel 4 lambda to reach the point B. So if you look at the path difference, what does it mean by path difference? S1b is the path traveled by S1 wave, S2b is the path traveled by the wave from S2. So what is the path difference? It is S2b minus S1b, right? That's called path difference, right? Because D1 minus D2, that's called path difference. So what is the path difference here? That is 4 lambda minus 3 lambda, that is equals to lambda, right? Keep it aside. Here remember the path difference came to be lambda. Let me erase the board and write down here once again. The path difference have come up to here as lambda. Similarly, from the second example, if you see S1 travel 4 lambda distance, S2 travel 6 lambda distance, the path difference over here is 6 lambda minus 4 lambda, that gives you 2 lambda. Similarly, third example here, the S1 has traveled 5 lambda, S2 has traveled 4.5 lambda, so path difference here is 0.5 lambda. What about point E? S1 has traveled 3.5 lambda distance, S2 has traveled 5 lambda distance, so path difference over here is 1.5 lambda. That means wherever you have a path difference that is integral multiple of lambda, integral means integers, right? Wherever you have a path difference equals integral multiple of lambda, there you have constructive interference. And where you have integral multiple of half lambda, I can write this as 0 plus half lambda. Here I can write as 1 plus half lambda. That means if your path difference is integral multiple of half lambda, right? Integral multiple of half lambda, you have destructive interference happening there. Clear? So we can make a note point. The note point is wherever you have a path difference equal integral multiple of lambda, those points are where you're going to have constructive interferences. So all these red lines, you stand anywhere on this red line, you see constructive interference. So either trough meeting trough, crest meeting crest, trough meeting trough, constructive interference. Similarly, you stand anywhere on this red line here, you are going to experience constructive interference because crest meeting crest, trough meeting trough. So conclusion is, wherever the path difference, so look at this here, m equals 2, 1, these are basically path difference value. Wherever your path difference is integral multiple of lambdas, there you have constructive interference happening. Constructive, constructive, constructive. But look at the point F. You can see crest meeting trough of a second wave because the path difference is 2.5 lambda. So wherever your path difference is integral multiple of half lambda, there you have destructive interference happening. Clear, everyone? I hope you understand the concept of where you have constructive interferences happening, where you have destructive interferences happening. So a point where you have constructive interference happening like m equals 0, 1, 2, these are called antinodal line, okay? Or a point on the line are called antinodal points, and this line drawn, red line, all these red lines are antinodal lines, but the point on those antinodal lines such as the point K, point G or point I here or point O here, these all are antinodal points. Okay, so antinodal points are the points where the wave undergo constructive interference. But what about the blue lines? Blue lines are the points where the wave undergo destructive interference, right? Look at those blue lines. Everywhere you have destructive interference happening. So these blue lines are called nodal lines, and the points on the nodal lines are called nodal points. Okay, so nodal lines are the lines on which the wave undergo destructive interference. Okay, so that's all about where two source causes interference. Yes, two source when cause interference leads to destructive and constructive interference. The line where you have constructive interference happening, antinodal points, and the point where you have destructive interference happening, nodal points, right? So that's what the conclusion we can make here. If the path difference is integral multiple of lambda, you have antinodal points there because constructive indifference happening there. And the path difference, if it is equal to integral multiple of half lambda, then those are going to be nodal points because that leads to destructive indifference. Clear? Now, why do constructive indifference happen at antinodal point and why destructive indifference happen at a nodal point? Simple answering to it, because look at this example here. From the source S1, the wave has traveled a total distance of 6 lambda to reach this point P, whereas source S2, this wave has traveled a total distance of 7 lambda to reach this point P. So if the wave has started from the peaks traveling 6 lambda or traveling 7 lambda or traveling 8 lambda or traveling 9 lambda, will always end up peak. So peak meeting peak, that is crest meeting crest, constructive indifference. Look at this example here. So S1 travels 6 lambda, that means starting with peak ends with peak, whereas S2 traveling 8 lambda starting with peak ends with peak. So peak meeting peak, constructive indifference. Look at the third example here. S1 traveling 6.5 lambda starts with peak, ends with trough. S2 travels 7.5 lambda, starts with peak, ends with trough. Then also trough meeting trough, constructive difference. You can see the path difference is 1 lambda here. Look at this example. S1 has traveled 3.5 lambda distance. That means starts with peak, 1 lambda, 2 lambda, 3 lambda and another half lambda. That means starts with peak, ends with trough. Similarly, S2 has traveled 4 lambda, that means starts with peak, ends with peak. If anyone have doubts, say why starts with peak and ends with peak, look at 4 lambda means 1 lambda ends with peak, 2 lambda ends with peak, 3 lambda ends with peak, 4 lambda ends with peak. So here peak is meeting trough, that leads to destructive indifference. So what is the path difference here? 4 lambda minus 3.5 lambda, that is 0.5 lambda. So this last example here, you can see S1 travels 4.5 lambda, that means starts with peak, ends with trough. S2 travels 6 lambda, starts with peak, ends with peak, leads to destructive interference because peak meeting trough. And what is the path difference? It is 1.5 lambda. So you can see all the examples here that wherever you have constructive interference happening, it's always a nodal point, antinodal point. What is antinodal point? Integer points are called as antinodal point. 1 lambda is antinodal point. 1 lambda again antinodal point. 2 lambda here antinodal point. So antinodal point and leading to constructive interference. Whereas 0.5 lambda, 1.5 lambdas are nodal points, right? So yeah, nodal points are the points where you have crest meeting trough leads to destructive interference. Okay, next. In your formula booklet, the condition is written like this. That's the constructive interference is when the path difference is integral multiple of lambda, where n goes from 0, 1 to 3 and so on. Similarly, destructive interference occurs when the path difference is integral multiple of half lambda, where n is equal to 0, 1 to 3. Okay, so let's do a problem. 2 point sources 3 centimeters apart are generating periodic waves. That's how the periodic wave. A point on the third antinodal line. So let's say this is n equals 0, antinodal line n equals to 1 and so on. Maybe there is a line here which is n equals to 3. Third antinodal line n is equal to 3 is called third antinodal line. Of the wave pattern is 10 centimeters from one source and 8 centimeters from the other source. So from source S1 that distance is 8 centimeter, whereas from other source the distance is 10 centimeter. Determine the wavelength of the wave. Okay, so S1P is, let's call this as S1, that point SP. So S1P is 8 centimeter, whereas S2P is 10 centimeter. That gives you the path difference because S2P minus S1P is called path difference, which is 2 centimeter. Since it is an antinodal line is where path difference must be equal to integral multiple of lambda. So path difference is 2 centimeter, which must be equal to integral multiple n equals to 3 times lambda. So that implies lambda is equals to 2 by 3 centimeter. If you simplify this, you must get 0.667 centimeters. Okay, next question. 2-point sources are generating periodic wave in phase. So I'm again considering two sources, S1 and S2, generating periodic wave. The wavelength is 4 centimeters, the lambda is given here. A point on the second antinodal line, so that's n is equals 0, and somewhere you have n equals to 2 antinodal line. Remember, antinodal line is where you have a constructive interference happening. How far is this point from the farthest source? So S1P is the nearest source, S1 is the nearest source to the point P, S2 is the farthest source to the point P. We know that the path difference, which is S2P minus S1P, should be equal to integral multiple of lambda, since it is causing constructive interference, because we are talking about on the antinodal line. On antinodal line, we always have only constructive interferences happening. So we have to find out how far is the point from the farthest, which is the distance S2P, which is going to be n lambda plus S1P. N is equals to 2 because second antinodal line. Lambda is 4 centimeter plus S1P is 30 centimeter, which is going to give you 38 centimeter. Okay, so farthest point is at a distance of 38 centimeter. Okay, so the last topic under 4.4 is double slit interference. So please note, if you understood the concept of double source interference, double slit interference is going to be easier for you to understand. Okay, I mean basically double source is two speakers, right? You have taken two sources. Instead of two sources, what I'm going to take, I'm taking one torch and allow the torch light to go through a small slit, like two slits, slit S1 here, slit S2 here. You can see, look at this, slit S1 and slit S2. From slit S1, the light is going to diffract because it's a narrow gap. Slit S2 also will have light diffracting. So basically double slit interference is double source interference only, because from this point, slit S1 and S2, those are two slits acting as two sources, right? So that's what I said. If you understood the concept of double source interference, it's easier for you to understand double slit interference. Okay, now when you see a double slit interference, let me take you through a simulation once. Okay, look at this here. You can see I have a small slit, a narrow gap, a small slit. I'm sending a light ray to go through it. You can see this pattern on the screen. Look at this pattern on the screen here, which is enlarged and shown on this region. So this is what I was telling you, right? When the light is passed through a small gap, you see multiple spots on the wall due to the diffraction. So this pattern is due to double slit. Okay, so two source, you can say, or double slit, the same thing. So when a diffraction pattern formed by two slits looks like this, okay, you're going to have a bright spot and then a dark spot and bright spot and dark spot, a bright spot and dark spot. But why do we have bright spots and dark spots? We have already learned that when two diffracted wave overlap, they cause interference, and interference may be destructive, may also leads to constructive. So regions where you have a constructive interferences, basically line called antinodal lines, bright spots because constructive, and all on the nodal lines you're going to have a dark spot because destructive. Clear? I hope you understand that point. Fine. So the distance between the central maxima, I'm going to call this as central maximum, that's the brightest one because that's the shortest distance one, and farthest one, why they become dimmer and dimmer? Because farther the wave travel, it becomes weaker, the intensity of the wave becomes weaker, and therefore the light becomes dimmer as it goes away. But the central one is the shortest distance from the slit, that's why it is always the brightest one. Fine, so this distance between the central one and the second maxima, I'll call it as n equals to 1 because first antinodal maxima, and this is your central maxima, n equals 0. So distance between two consecutive maximas, the distance between two consecutive maximas is called as fringe width or fringe distance or fringe separation. So let us derive a formula to calculate the fringe separation. If you know the wavelength of the light, in this example you have 380 nanometers, right? If you know the wavelength of the light and if you know the slit separation, how do you find out, how do you calculate the fringe separation? What is meant by fringe separation? Please note down. Fringe separation is the gap between two consecutive maximas. Okay, so let me draw it on the board here. Okay, so I'm taking light. This is my one source of light, like a torch light passing through two slits, narrow slits. The wave is going to diffract like this, and on the screen you're going to have consecutive maxima. So this is my central maxima, and then n equals to 1 maxima, then n equals to 2 maxima, n equals 3 maxima. So you can see I'm just showing a dimmer one here because it becomes weaker there, because light has to travel a longer distance to reach there, becomes weaker. But whereas the central one is the shortest one, or the very nearest one, that's why it is the brightest one. Okay, so if I have to draw intensity versus distance graph, that's how the graph looks like. Okay, so at n equals to 0 you have a largest intensity or the maximum intensity, n equals to 1 you have a slightly smaller than that, and so on. And this pattern will be same on this side as well, right? This pattern which is drawn on the screen is called as interference pattern. Okay, double slit, you can also say double slit interference pattern. And this experiment was conducted by scientist Young, or physicist Young. That's why it is also called as Young's double slit experiment. Okay, Young's double slit experiment. So I said we have to derive an equation, right? What is the equation for? So I'm not going to draw this diagram, which is going to look like very complex. I'm calling this as slit S1, and this is my slit S2. Slits S1 and S2 separated by a distance small d. Okay, and we have a central maxima forming at point O. Why central maxima? Because that's the shortest distance, and path difference here is 0, where we also called as antinodal point, where n is equals to 0. Similarly, I'm talking about another point P there, because this is my central maxima, but we are going to have another maxima somewhere else, right? This is how the interference pattern looks like, right? So we are going to have a maxima at P also, and the distance between P and O is called as fringe distance or fringe separation, small s. Okay, fringe separation, small s. So from the mid of the slit to this central, I'll call that distance from the slit to screen, I'll call this a screen here. Screen is basically on which you are seeing the interference pattern. So this is my slits, and that's where my screen is, okay, on which I'm seeing this interference pattern. The distance is called as capital D, okay, or screen separation, you can say. Now, so I'm assuming this angle over here, I'm just joining a line from, you can call this point as A. I'm joining a line between A and P, and I'm calling this angle subtended here as theta. And I'm dropping a perpendicular line from S1 onto this line, okay, onto my source S2. So S1 P is the wave distance traveled by source S1. S2P is the distance traveled by the wave from source S2. Now this is the extra distance. This is the extra distance the wave from S2 has traveled to reach P, and that extra distance is called as path difference, right? So I'm writing down here path difference, which is S2P minus S1P. What is S2P minus X1P? I'm calling this as X. So that is X. So path difference is equals to X. And we have learned that at P, what is happening? Constructive interference. We have learned that wherever there is a constructive interference, the path difference must be equal to integral multiple of lambda. So n lambda must be equal to X from above to equation, from equation 1 and 2. N lambda must be equal to X. Since we are looking at point P where n is equals to 1, substituting n equals to 1, lambda is equals to X. That's my equation number 3. Keeping aside, now come back. From the triangle APO, we can say sine theta is equals to opposite, which is OP, divided by hypotenuse, which is AP, right? But while deriving this equation, Huygens has made an assumption. The assumption he made is that the screen distance, which is capital D, is much larger than the slit separation, small d here. Okay, due to which the theta is very small. So why is theta very small? Very basic understanding. Look at this. Say there is a screen and I have a random point P on it. From here I'm observing that point P. So I'm making an angle theta. What if I just push the screen to here? P will remain on the same point on the wall, but angle subtended on my eye will now be smaller. Right? Theta 2 is smaller than theta 1. If I've pushed the wall even further away, so P will still be there on the same spot on the wall, but angle subtended on my eye will be even smaller than theta 2, which is theta 3. So that means farther the screen is from the eye, smaller the angle will be subtended at the center. That is what I was talking here. That this D, the screen is very far away from the eye. Slits are eye, you can consider slits as eye. So screen is far away from the eye. Therefore, this D is much larger, very big. That is why theta is going to be very small. So since theta is too small, you can, what happens is, look at this line, this straight line and this line approximately becomes equal length. So instead of this hypotenuse AP, I can replace hypotenuse with base value AO, because this length is approximately equal to this length since theta is very small. Please remember, Young's double slit experiment, assumption is made that theta is very small. And why theta is small, I will clearly mention that the screen is at a very far distance from the slits. Okay, now from this I can write down sine theta is equal to OP, which is fringe separation small s, divided by AO, which is screen distance. Since theta is small, sine theta equals to theta s by d. Okay, so I'm writing this as equation number 4. Okay, now come back. Since this is theta, this is 90, this is 90 minus theta. If that's 90 minus theta, that's going to be 90 minus theta. I'm writing down here, that's going to be 90 minus theta. And since this is perpendicular line drawn here, this is going to be theta. I repeat, this is 90 minus theta. This is going to be how much? Theta. So from triangle S1, S2, let me call this point as W. From right angle triangle S1, S2, W, sine theta is opposite, which is x, this is opposite side because it's also 90, divided by hypotenuse, which is small d. Since theta is very small, theta is equal to small x by d. This is my equation number 5. So from equation number 4 and 5, I can write, x by d is equals to s by capital D. And from equation 3, I can say x is equals to lambda. I replace x with lambda. So lambda by small d is equals to s by capital D. That implies fringe separation small s is lambda into capital D by small d. So this is the equation derived by Young's double slit experiment, which says that slit separation is lambda capital D by small d. So from this equation, what we can say, that larger the wavelength, larger the slit separation. Okay, we'll see whether that's true or not. Look at this, larger the wavelength, larger the slit separation. Look at that, look at this maxima and this maxima. Now distance has increased, right? Now when I'm decreasing the wavelength, that gap distance between two maximas has been reduced. So larger the wavelength, larger the slit separations. Similarly, from the formula, larger the screen distance, larger the slit separation. And finally, if slit separations are greater, results smaller fringe width. Please note S stands for fringe width. Okay, so larger the slit separation, smaller the fringe width. Okay, that's what observation we have made from the formula, and also I showed you through simulation there. So that's all about Young's double slit experiment, which is also double slit interference pattern. That's the formula given by him, S equal lambda d by small t. So let's do this problem here. Use a graph given below for this question. In double slit interference experiment, the two slits are separated by distance. Two slits are separated by distance, which is small d here, and the screen is capital D from the slits. Determine the wavelength of the light used in the experiment. Okay, so do I know the fringe separation? Yeah, because the distance between two consecutive maximas is called fringe separation. So from this maxima to this maxima is 0.5 centimeters. So small s is 0.5 centimeter. That's called fringe separation, right? Distance between two consecutive maximas is called fringe separation. Small s 0.5 centimeter. And small d given as 4.2 times 10 power of 5 minus 4 meters. Let me convert that also in meters. 0.5 times 10 power of minus 2 meters. Capital D given as 3.8 meters. Everything is given except for lambda. So from the formula S is equals to capital lambda D by small d, I can write lambda is equal to S into small d by capital D. So we plug in all the value and get the value of lambda. I'm not doing it, you can do it on your own. Next, suggest the effect on the separation of fringes of decreasing the wavelength of the light. So question is, what is the effect on the fringe separation or separation of fringes when you decrease the wavelength of light? Obviously, when you decrease the wavelength of light, fringe separation will also decrease. Next question, state the feature of the graph that enable you to decide the slit width is negligible. Please note, when slit width is negligible, what happens when the slit width is negligible? You're going to have a purer diffraction, right? When slit is negligible, purer diffraction, due to which the rays goes in every direction, right? That is why the wave reaches to farther distance and makes the intensity to be approximately same throughout. But what if the slit width is not negligible? Then the wave diffraction is look like this, due to which most of the waves goes straight, very smaller wave goes onto the corner sides. Because lesser wave goes to the corner sides, the intensity decreases, where intensity increases in the center and again intensity decreases. When you see the intensity is uniform throughout, that's only possible if the slit width is negligible, right? We have already discussed under Huygens and Fresnel principle. If the slit width is negligible, you're going to have a purer diffraction. You're going to have a purer diffraction that will allows the wave to go in all the direction of equal magnitude, right? Yeah. So that's it about 4.4.